Let's continue. And let me make a little programming note that the way I structure this, there's a lot of stuff that goes into these direct solvers for integral equations. So the way I've structured this is that I am going to cover most of it today. So today is a little bit fast. But then we have 2 hours tomorrow, and I'm basically not going to introduce any new material tomorrow. We're just going to go back and revisit and talk more about the functions of these basis matrices, different physical interpretations, different formulations of the same scheme. So yes, so we're going to introduce a fair amount of material today, but then essentially no new material tomorrow. We're just going to repeat these concepts and look at them from different angles. Okay, so we've described this technique for reducing the block size in a blocked linear system associated with an integral equation. And the question now is, how do we get a linear complexity scheme out of this? And we're going to proceed just as we did in the discussion of the fast multiple method, and we're going to recurse. So now let's start with a matrix blocked into 8 by 8 blocks. So we do this compression scheme that we just described. And now what I'm going to do is I'm going to merge these blocks. I'll take these blocks, and now I'm going to merge them in pairs. So we are now so in the example shown, we started with a 3-level partitioning. So now this would be the 8 block, and this is the 9 block. So I just group them together. I join these blocks in groups of 2 by 2 to get the level 2 representation. Okay? So this is up here. Notice now that the diagonal blocks of the diagonal blocks in this matrix are the artificial ones, the ones that I numerically computed. Everything else is just a submatrix of the original matrix that we started with. So it turns out that the off-diagonal blocks here, they have exactly the same structure, because notice that the off-diagonal blocks are untouched. They're just submatrices of the original coefficient matrix. So everything we've said about compression, you know, rank decay for Laplace kernels, for Helmholtz kernels, all this stuff applies to this matrix as well. The only difference is that I've thrown out some of the degrees of freedom, and I modified the diagonal blocks. Other than that, this is really the same system as the big one. It's the physics in the ranks of the off-diagonal blocks is the same. So I'll take this one, I'll compress it. Now I'll end up with some new diagonal blocks. But again, the off-diagonal blocks are just subselections. The only thing that's happening here is constructing new diagonal blocks and throwing out some of the indices. So now reblock here to get up to this system, and you just keep going. And then hopefully at some point you end up with a system that's so small that you can drown it in the bathtub, so to speak, and just do a brute force inversion. Okay? So if you prefer to look at this from the point of view of matrix factorizations, you can look at it like this. So the original matrix A, if you look at the block separable factorization, then recall, so now we're looking at an 8 by 8 block matrix. So we have this, we pull out the diagonal blocks, that's over here, and then we have the U matrices and the V matrices. So these are on level 3. So the superscript here refers to level. So now all of this stuff is the matrix of off-diagonal blocks on level 3, the finest level. And now my claim is that after reblocking, that matrix itself has exactly the same rank structure. So I can do the same factorization of that one. So we pull out the diagonal blocks. That's now this matrix, and have these flanking basis matrices. the U matrices on level 2 and the V matrices on level 2. And you just keep going. Right. So then there's a formula, just by applying Woodbury recursively. The inverse of this formula is this formula. So again, a telescoping factorization. And notice that these things are again very similar to, you could view the fast multiple method as a telescoping factorization as well, where these various matrices correspond to, so the V matrices are really the outgoing to outgoing expansions. The U matrices are the incoming to incoming expansions. And the, what I call the B matrices here, these are the ones that have the a tilde sigma tau. So it's the compressed interaction between matrices, between patches sigma and tau. So the main difference to the FMM here is that there are no interaction lists. I compress boxes that immediately touch. So the interaction list is very short. The interaction list only has one element. Somebody talks only to their own sibling to exchange information. And so you talk only to your sibling, your child, your children, and your parent. That's it. All right, so now let's formally define this. So a hierarchically block separable matrix, it's based on exactly the same tree as we introduced for the S matrices. And as it happens, so one of the things we're going to do tomorrow is we're going to revisit this definition of HBS matrices and discuss the fact that so every HBS matrix is also an S matrix. So it's a special class. So there's actually a strong connection between the two representations. So you get this hierarchical format by making some additional assumptions, and we're going to talk about that in detail tomorrow. Okay, so now the assumption is really quite simple. So on the leaves, so for this, at the smallest blocks, we simply make this assumption that we talked about earlier this morning, that each off-diagonal block has low rank, and there's this property of being able to use of reusing the same basis matrices for each row of blocks and each column of blocks. So then on the parents, on the higher levels, we make exactly the same assumption, just that we need to reblock. So what's going on here? So this is really here. So I compress on the leaves, and then I reblock. So each off-diagonal block here is what's entering there. So this is a block pre-compression on an intermediate level. And then my assumption is that this merged block has precisely the same type of representation as I made the assumption for the leaves. All right. So there's a lot to process here, and I would strongly encourage you to look at the codes, because the codes turn out to be quite simple. We're going to revisit this tomorrow, exactly what's going on here. But the upshot, just to give you some happy news, is that the end representation is really quite simple. So we have, in order to specify a matrix in the HBS format, you really only need to specify these things. So for each matrix, for each block, tau in the tree, you need to specify these small basis matrices, U and V. They're small. And they represent, again, they're analogs of outgoing to outgoing translation operators and incoming to incoming translation operator. That's what they are. On the leaves, I need to specify the matrix D, which is self-interactions. And for parent nodes, I need to specify what I call here the matrix B. So this corresponds to the outgoing to incoming translation operators in the FMM. Just here, the interaction list is very short. And then the algorithm for inversion, once you have all these factors, the inversion algorithm looks just like this. Notice that this is really, it's a very clean algorithm. And this is the corresponding MATLAB code. So this code you can download. And you can compare and see that even though the presentation here probably seems a little bit dense, the resulting codes are actually very clean. Notice that this is particular. This is what happens when the underlying domain is one-dimensional. You can apply this simple scheme in higher dimensions, but then you have to pay a price. And then if you want a fast algorithm in higher dimensions, it gets more messy. In that case, I will make no claim that the codes are simple. They're not. But, right. So this is the code. Download it, play with it. So now the big question, or a main bottleneck in this development has been to find, how do you find these basis matrices in the first place? How do you find the skeletons? So before I describe how to do this, let's just revisit so we remember what are the functions of the U's and V's. I guess I forgot to turn my phone off. I apologize. There we go. Right, so what are these? So the matrix U4. So tall, thin matrix. Its function is to span the columns of the off-diagonal blocks in the first row. So like this, right? This is just a repeat from an earlier slide. And the same thing as you go down. So how do we compute them? We're going to use the interpolative decomposition. Let's just briefly remind ourselves about the interpolative decomposition. So we introduced it in the context of mapping a source distribution, a collection of sources, to a set of targets. There's some matrix here that maps you from one to the other. And skeletonization really, what it means is that we find a subset of k column indices and k row indices. So these index vectors correspond to subselections of the source locations and subselections of the target locations. So now the physics is that given a set of sources on all these points, I can project these onto sources on just the red points. And that's really my outgoing expansion for that box. It's a compact representation of the sources in here. And then I map it via the original interaction kernel. So A12 is all entries of A12 look exactly like this for red and blue points. And then the physics is that if I detect the potential only at the blue points, then I can, to my preset accuracy, interpolate to all the other points. So I only need to look at the potential at these blue points to know where it is everywhere. Okay, so this is the physics. Right, and just a little reminder, recall that an advantage here is that it's a numerically constructed representation. So we can do a lot of things that we can't do with analytic expansions. So we can compress adjacent boxes, for instance. We can take advantage of, so this is precisely the situation we're in now, that if you're on special geometries, the rank is much lower than the general rank. So if you view, for instance, if you take the mathematical operator that maps, a source distribution in this box to a target, to a potential in this box, it's a much more complicated object. But here we have, there's some band limiting going on that's specified by the grid spacing. And then we also have restricted geometries. So the numerical ranks are much lower.
Gunnar, sorry.
Yeah.
On the previous slide here, are you going to discuss
this one?
Yes, how the rank grows with the sort of the length of the touching
of
the boxes? Is that related?
Yes, absolutely.
Okay. All right.
All right, so now let's talk about how to actually compute these basis matrices. Right, so first we partition. So in this case, just for purposes of the graphics, it was most convenient to partition into 16 leaves. And I want to compute, so I hope everybody sees, so there's a little section here that's marked in red. So I want to skeletonize the interaction of this little guy with the rest of the world. So specifically, I want to construct the basis matrix U. So U, recall, is an extension operator, that if I know the potential at some subselection of these points, I can interpolate it to all the other points. So I need to compress this big matrix. So this big matrix marked in red over here, that's the matrix that takes a source distribution on the black nodes and maps them to potential on the red one. So really, mathematically, what I need to do is perform Gram-Schmidt on the rows of this big matrix. This is expensive, right? Because n can be very large. So what do? I don't want to even build this big matrix. If I do, then I'm cooked. Then I'm n squared immediately. All right, so we can, we talked a lot about localization, that interactions are short range. So maybe we can just forget about all points that are far away. So the green nodes here will certainly interact strongly with the red nodes. So let's keep them. And then maybe we can just hope for the best and forget about the far field. This doesn't really work because there's no way that by placing sources on these green nodes, I can emulate any possible incoming potential on the red ones. But what I can do is that I can introduce a few extra points that were not part of the original discretization. So by placing these proxy sources on this circle, I recall that this is exactly what we were talking about in lecture 3, about how to numerically construct representations of all possible well-separated points. That we had these representation formulas for, in this case, Laplace potentials, and that's exactly what I'm exploiting here. That by placing sources on these green nodes, I can really, to the preset accuracy, replicate any potential caused by far-field sources on the red target nodes here. So notice, of course, that all this is to some finite precision, so you specify a precision, and then there are some tuning parameters here. How big do you choose this circle to be, and how finely do you sample it? So these are things you have to think about a little bit, but it's not that complex. Okay, so then in the end, what we do need to compress numerically, so we do need to explicitly compress the interaction with the close-in nodes. Right, this is idiosyncratic. Whatever setup you're given, any specific patch has its own little local geometry. I have to process that. I cannot use any clever tricks for that. But then I can replace all far-field interactions by adding this little extra, what we call a proxy matrix G. So now I form a much smaller matrix B, and this is what I execute Gram-Schmidt on. So now I execute Gram-Schmidt on the rows of the smaller matrix B, and that will give me both the set of index nodes that I want to keep. So this is what I'm doing there. So now these are the ones that were kept. So there's an index vector that points to the red nodes here. So I compute that one. That's the output, one output of the Gram-Schmidt process. And the other output is this interpolation matrix that tells me, given the potential on these red nodes, how do I interpolate back to all the nodes? Any questions? No. Okay, so now you just continue, you compress box by box.
Quick question.
Yeah.
So I would guess that you could sort of achieve the same end by basically using harmonic representation on that cylinder proxy surface as well, but the disadvantage there would be that you're sort of introducing new mathematics, whereas this is still using essentially your matrix kernel A.
Yes, that's exactly right. So there are many ways of doing this. Instead of, this is not the only, so instead of using these proxy sources, what I could do, so we have this contour, so I'm compressing this little subpiece gamma. Now I put proxy sources here. Alternatively, I could use that any potential caused by sources outside this circle, it's harmonic. So I could just take this box and use a local harmonic expansion there and say that any potential, any possible far field, any possible potential caused by the far field sources can be replicated by introducing, say, 20 local harmonics here. That works perfectly well.
The nature of my question was sort of more about, this seems sort of well suited for Nyström, but maybe less so for Localisation techniques, because you cannot, or at least not very easily, construct the mesh or testing functions that would be your proxy set.
Right.
You say the nature, yeah.
Yes. I believe, but I haven't actually done it. I think you can still do it for boundary element discretizations, but this is really based on
sort of at runtime making shells of elements that you put proxy test functions.
Everything is set up very nicely for Nyström. Okay. Like all codes we have are based on Nyström, so the whole machinery is developed for that. I think it can be extended to boundary elements, but that's a conjecture.
I think it would.
In practice, can you do this? Do you just do this with, I guess, QR on the transpose of B?
Yes.
Okay.
Yeah.
It stays small all the way up.
Right, QR, or, I mean, I like the randomized. I like the randomized SRFT.
Yeah.
It's, but if the matrices are small, it doesn't really make much of a difference. Yes?
So you could as well do the randomized ID on the whole B, the Offdiagonal plus.
No, because the randomized ID, so recall, so if I want to compress a matrix of size, so in the lecture, the matrix was of size m times n, times then log of the rank. So the reduction in complexity is on the rank. I still need to form the entire matrix. And in this case, the main issue is that I don't even want to form this matrix. I never want to even compute these kernel, do these kernel evaluations. Because in that case, I at some point have to compute every single entry in the coefficient matrix. I don't want to do that.
But wasn't there a math state part that you chose a random vector and multiply? Does that still involve the full formation? I'm not.
Yes. Yes. For the SRFT, the idea is that you're given a dense matrix with no structure in it. And that matrix is just represented as a full array in RAM. Yeah. But so the randomized techniques can be used on this small matrix B. Right. I mean, you can use the basic randomized method sort of in the same spirit as you use the Krylov method if you have a fast matrix vector multiplier. So there are some situations where you have a way of rapidly applying the matrix, but in that case, it's a completely different compression regime. If I get time, we'll talk about it tomorrow. It's one of my optional topics. Right. All right. So basically, when we processed all the leaves, what we've done is that we've discarded a bunch of internal nodes to each leaf box, to each leaf panel. So then I group the panels in two. I take two leaf panels, I group them together. Now I have some points that used to be boundary points, they're now internal points. And I compress them, I get rid of them using exactly the same technique. So everything works the same. All right, so in the end, it looks like this. So one thing I greatly like about Nyström is that it's very easy to produce Nyström and using interpolative decomposition. So it becomes very easy to produce these pictures where you show the skeletons on each level. So this is after level 3 compression, after level 2 compression, after level 1. And at some point, there are so few points remaining that you just, by brute force, invert. Okay, so in real life, it gets a little bit more complex because typically, so the previous slides were for the single layer potential. You know, it's just the log kernel. Typically, potentials are non-symmetric. Sort of the incoming things and the outgoing things look a little bit different. So here is, for instance, a double layer potential. So it's a non-symmetric kernel. And in this case, you have to modify the techniques a little bit. So we're compressing. Let's see, so the incoming compression works. The compression of the red box works exactly like it did for the single layer potential, but I'm really just wanting to compress all possible incoming fields. So whether the source is out here, whether they're dipoles or monopoles, it doesn't really matter. I can represent the field anyway using monopoles on the proxy surface. But now doing the other block becomes a little bit different. So now I want to compress, this is for the outgoing expansion. So I want to find a way of constructing reduced sources, a reduced representation of the sources inside the block. And now I have to explicitly think about the fact that this is actually dipoles. So I have to place dipole sources inside here, and you know, there are some things to think about here, but conceptually everything works the same. All right, so there are a few things that I've been, there's one thing I've ignored at this point, which is, but notice that if I do things the way I described now, you skeletonize first the big row blocks and then the big column blocks, then I might end up choosing two different sets of indices for one box. It turns out this is actually fine. You can construct direct solvers and allowing that to happen. But I personally get very confused by this. So I like to enforce that these 2 points are the same. You can do this. If you just modify the algebra a little bit, it's really you're simultaneously compressing this block and that block, then you can make sure that you pick the same points for both the incoming and the outgoing skeleton. It leads to some very mild suboptimality. Maybe the ranks increase by 1 or 2 or something, but to me, it just simplifies life a lot. Right, so another thing I've ignored is quadratures. So recall that near interactions here are not through the original kernel, because I have to modify the matrix elements. So this caused some complications. They can be handled. I mean, if nothing else, you could just apply the direct solver to a matrix that has the original kernel and then view the corrections as a very sort of near diagonal in physical space, small correction to that matrix, and use a very fast iteration on that. But you can actually do better things. You can just handle the actual matrix in the compression. For Helmholtz, things complicate a little bit, and we discussed what to handle. So the problem here is possibility of resonances. So sometimes putting monopoles on the proxy surface is not good enough, but this is very easily fixed. I mean, the easiest thing is to just make sure that you don't pick the proxy surface at a resonant frequency. Otherwise, you can take 2 sets of proxy surface that are a little bit separated. There's a variety to get around this. For other elliptic PDEs, this most analogous things can be done. For most of these, it has been worked out. Some cases are remaining. And this final point. You have to think a little bit about how finely to sample the proxy surface. For Laplace, it's very easy. You just do it once at the beginning of the code. But for Helmholtz, it's a little bit more tricky because the number of points you need on the proxy surface, it has to resolve the wavelength. So once the proxy surface starts to get large in terms of wavelengths, you have to increase the number of points proportionately, which of course means that the rank will grow in that case. So the method will start to bog down if you do it for smaller and smaller wavelengths. All right. So the situation I've described so far is it's particularly easy and benign because the underlying geometry is really one-dimensional. So for a curve like this one over here, you can just do the partitioning. There's a number of things in which this simplifies life. So one is that you can just enumerate the points consecutively along the curve, and this sort of roughly corresponds to distances in physical space. If you try to do it on a contour like this, so in this case, gamma is the union of all these blue ellipses. So in this case, you can improve the situation by using things like volume filling curve orderings and this kind of stuff, but you cannot completely resolve this. So in this case, what you want to do is you want to put the binary tree on the physical domain. So now we declare this to be the root of the tree. We split it in 2 halves, 2 and 3, and then continue splitting recursively. So the box 2 gets split into the boxes 4 and 5, and so on, going down the tree. Okay, so compression works the same, basically. You just have to think a little bit about how to place the proxy sources. So if I want to compress this red box here, so it's a subpart of the domain, at first it looks like I need to form the matrix that maps sources on all the blue points onto targets on the red points. This is a very large matrix. I don't want to even form it. But we do exactly the same thing. We forget about the far field, by placing a proxy surface around it. So in this case, this is purely an optimization. How closely, how snugly do you want to place the proxy box? So in these examples for Laplace, you typically want to place it fairly close. Then you keep the near field, you explicitly compress that. And then you replace the far field by sources on the proxy. Okay? That's what happens after compression. Yeah?
Can you explain more about, like, how do you adjust the charges on this proxy box? Like, what is the value of the...
So what I'm looking at is the map. I'm not doing this for a specific set of charges in the proxy box. What I'm looking at is a map. So there's a, in this case, there's a matrix that maps a source distribution, a dummy variable basically of sources on the green points onto potentials on the red points. So I'm forming that matrix that maps a given source strength on the green points. So it's the matrix I'm looking at, not for a specific source vector.
I have a question. Is the point one written on evenly distributed, or you have some special distribution?
Evenly typically works very well, but it's pretty insensitive to that. You can put Chebyshev nodes on these lines as well, or Gaussian nodes, or anything that samples smooth functions nicely.
I think it is, it's really oversampled to begin with, so it's going to be decimated to some totally unstructured collection.
Right. We start with oversampling, and you know, I like to oversample by about a factor 2. Yeah. That's safe. It costs a little bit, but I'm willing to trade some runtime in favor of stability and just knowing that things will work. Okay, so this is what the overall process looks like. Here we have the original set of points. We skeletonize the leaves, then we merge them in groups of 2, then skeletonize. And notice that here, yeah, so you get these aggregations of points. This is important. But notice how the points really collect along the interfaces. Like this. So the good news here is that the algorithm that we described for a simple curve in the plane, it works exactly the same for these two sort of more evenly distributed in the volume sets of points. You can run exactly the same algorithm. You just need to rewrite the few lines that describe the proxy surface. How do you design the proxy surface? That you need to change. But otherwise, the code is exactly the same. So the bad news here is that the ranks grow. As the box sizes get larger, you start to get these aggregations of points along the boundaries, and we no longer have linear complexity. So let's think about it. How many points do we have? Suppose you have a fairly even distribution of collocation points in a box, and now we're looking at some subset omega tau. So if we have m points inside omega tau, then you're going to find, this is something I'm just telling you, you can verify this for yourselves, but the points aggregate in a thin layer around the boundary, and the width of that layer is essentially fixed. It depends very weakly on the accuracy. So you get an aggregation of points along the boundary, and it's really, the rank is proportional to the number of points that survives, and it's going to scale as root m. So these matrices that I say are small, but they're not that small. They have size root m, and I need to perform dense operations on them. So the complexity required to process a box Oh, did I switch points here? Switch notation, what do I? N tau is what I call it. Like this. So now if you execute the complexity analysis, I think you believe me if I say that it's going to exactly mimic the analysis of nested dissection, that the most expensive part of the entire computation is processing the top level. So at the top level, n tau is basically equal to big N, the total number of points. So I have root n points surviving at the top level. I do dense stuff to it, and the complexity is n to the 1.5. And basically, if we next look at a simple surface in R3, it's going to look basically the same. So now how do we compress this? So now I'm going to put a tree in parameter space. So here's this torus-like surface. It's not exactly a torus because I didn't want it to be rotationally symmetric. So we parameterize it. So notice now, so now we're doing this thing where, surface in parameter space, we put little triangles, and then there's some sort of parameter map that brings you up to the surface. In this case, it's an analytic map. It's a map that I just specify. I made something up. But in general, these are numerically specified. So, the surface is represented by some fixed order polynomials over the triangles, oftentimes piecewise linears over the triangles. But this is the general idea. Right. And for a simple surface, you can put the tree in parameter space. So this problem, it's really sort of two-dimensional. The geometry, the intrinsic geometry is two-dimensional here, even though it's living in three-dimensional space. So I put the binary tree in parameter space. I cut the longest size of any box. So notice that everything I described, it works perfectly fine for adaptive trees. It's, when I describe the HBS arithmetic, when I introduced it, I had uniform trees. Right? On the leaves, I cut the index vector up into basically equispaced things. Let's actually go back and verify this. Let's look at the algorithms. This is instructive. So here, there's no referencing of the levels here. So I can perfectly easily have an adaptive tree. The algorithm will look exactly the same. The only thing is that you have to order, right? So there is a reference to the level, but this is a little too strong. I wrote it just as a simplistic shorthand. The only point here is that you have to process the children before the parents. So you can traverse this tree in basically any order. The only thing is that when I process this node, I have to have done everything below it. All right. So this is something that's very nice about this algorithm. Adaptivity is very easy to handle. One situation where adaptivity will bite you a little bit, I should say, is this step. Because notice now that the near field, once you're no longer at the leaves, I have to somehow find the near field points that survive inside the circle. But there's a caveat. I'm only looking at near field points that survive the finer levels compression. So in order to do that, I actually have to, so this is a slight violation of what I just said. But in order to process this box, it's not enough to have only processed its children. I also have to have processed its siblings. So this is something you have to think about a little bit if you have non-uniform trees. How do you find the near field points that survive? Of course, you can be lazy and I'll just include all the points, all the original points. And that will give you perfectly good accuracy, but it will not be very efficient, because on the high levels, you'll have a tremendously large number of points surviving in the near field. Right. So this is something that it's a little bit of a headache to code, but you can do it. Right, so we're doing this binary tree in parameter space in this case. All right, so now let's think about how to do compression. So we're isolating some little subdomain. I want to compress interactions between this red little patch and the blue. Far away from it. Now, what used to be a proxy line has to be a proxy surface. So I find an enclosing sphere for the red box, and then I extend the radius a little bit and place as my proxy a surface with a slightly larger radius at the same center. And then what I need to compress are interactions between the original interactions between the red triangles and the blue triangles, and then also between the red triangles and the green triangles. But I forget about the far field. So the gray part of the contour here is completely not engaged in the computation. It's a purely local computation, like that. So we skeletonize. So this is a very low order scheme that I'm showing here. Okay, so now we get this little cartoon. So after skeletonizing all the leaves, we've eliminated some interior nodes in each leaf, and then we merge them by pairs. So look what happened here. I have this leaf and this leaf. I merge them to form a bigger leaf on the next coarser level. And now these points are internal to the bigger, to the union, and they go away. To me, being able to produce these graphics is almost a reason to use Nyström in its own right.
I think that figure would be easier to understand if you did back based on the gather of the search on the based camera. Because I feel like you're looking through it and seeing sort of the holes on the other side too.
Yeah.
Okay. I just make sure I'm interpreting correctly.
Yes, no, I could have. I could have done it for an open surface, I guess. Yeah. Right, but so this is what it looks like. And you get fewer and fewer points. At some point, you just invert by brute force. But observe that, there are fewer points, but in the general case, there are root n points surviving at the top. Okay, so this is the same figure in parameter space. This will perhaps clarify things. Okay, done. So this is what it looks like. Okay, so before the end of the day, so tomorrow we're going to talk a little bit about, so notice that these schemes that I described, they have linear complexity if the underlying domain is essentially one-dimensional and the wave number is not too short. They have, if you have a volume-filling set of points in 2D, or you have a simple surface in 3D, the complexity is n to the 1.5. So tomorrow we're going to discuss a little bit how you can improve that. At a very superficial level, though, I promise. But before we close today, let's talk about one more equation. So we're going to talk about a volume integral equation. So these are a little less common than boundary integral equations. So this is the same problem that Adrianna discussed yesterday in the lecture about this Poincaré-Steklov scheme. So here we have an acoustic scattering problem in the plane. We have an incoming wave V that comes in hitting a region. So we have a plane wave that comes in. This is V. And then you have some region where the wave speed varies. So we're thinking, say, constant speed, say it's acoustic scattering, constant speed of sound, except in some little domain, a finite domain, which is the support of this function B, which you call it slowness. Yeah. Right. So B.
V3 over Vx is the slowness, I think.
Right.
That's
Yeah.
So, first of all.
So B here indicates basically the deviation from the free space. So if B is 0, then at x, then the wave speed is the free space wave speed. But it deviates in some region. So then this is the set of governing equations. You have the radiation condition at infinity, and then really a variable coefficient Helmholtz equation that we need to solve for x. But notice that it's variable coefficient only in a finite region. So now the standard technique for doing this, so the standard trick in scattering is really that you can convolve this with a free space fundamental solution. And another way of a very similar way of doing it is that you can look for a solution that is a convolution between the free space fundamental solution and an unknown source distribution. So suppose that the scattered wave is given as a superposition of fundamental solutions weighted by this unknown source distribution, Q. And then as it happens, Q will be supported in the same domain as B. So once you do this, everything reduces to an integral equation that lives on the support of B. So you put, what's my notation? Right, so omega is some domain that encloses the support of B. And you can convert this PDE now, which has the radiation condition, it has an infinite domain, etc., into a second-kind Fredholm equation. So in scattering, this is a very handy mathematical tool. You can now start doing series expansions and stuff, asymptotic expansions of the integral equation. But you can also use it for numerical work. But it's a very, if you want to really compute reliable, high-order accurate solutions, then you should use our wonderful Poincare-Steklov scheme, but you could also alternatively solve this integral equation. So it's a volume integral equation. And in this case, we don't have any reduction in dimensionality. The original problem is set in 2 dimensions, and the integral equation is set in 2 dimensions. And the reason you might want to do this is really that it's a very nasty problem to solve. It's hard to get high accuracy out of this. All right. Notice, incidentally, that even the ones without a body load, these integral equations, you can think of them in the same way, that it's some sort of analytic preconditioning. So if you take a homogeneous PDE, you can view it as convolving with the then you convolve with the free space fundamental solution, and then you get 0 everywhere except along the boundary. There's some jump. So the surviving equation lives only on the boundary. In this case, the surviving equation lives at the area where B is non-zero. All right, so we can design a direct solver for this integral equation. And in this case, this is again is really a volume problem. So you should do a binary tree in the volume. I discretized using the trapezoidal rule with some modification. And then the matrix elements will look like this. We use the proper weighting. And the question now is, how do you compress? So we have exactly the same situation as before. And I'm sure you can guess what this would look like. You put a proxy set of points that replace all far-field interactions. And then we only need to compress a small matrix inside. Now, as it happens, Lippmann-Schwinger is a little bit special. So you actually don't even need the proxy sources. The blue points in that case will necessarily serve as proxy points. And there are more interesting things. In this case, the integral operator is a little bit special in this case. So you see that this is a translation invariant integral operator. So it turns out to be very cheap to compress it. You only need to compress 1 box on each level. All right. Let me briefly mention some alternative approaches. So this will conclude. Once I'm done with this, we're done for today, and then we'll come back and revisit some of the topics tomorrow. So these H-matrix methods we mentioned a few times, you can certainly use to construct direct solvers. In that case, that community have not been using this green localization technique that I've been describing. Instead, they're using something called adaptive cross-approximation, which sort of seems to work. I believe it's less reliable. We can talk about that offline. Another thing you can do, let me mention this because it's an interesting idea, is that, so we talked about the FMM as a matrix vector multiply. Now, what you can do is you can roll out this structure. So you can introduce a new linear system that has as its unknowns not only the vector of sources, but also all the vectors of outgoing and incoming expansions. So we greatly lengthen both the source representations and the potential representations. But then you can write the entire FMM structure as a very large sparse matrix, a block sparse matrix, where the blocks here are now all the various translation operators. So you populate this matrix by plopping in all the translation operators. Now, this is a block sparse matrix. So you can just feed it to something like OMFPAC or one of these nested dissection packages, which are extremely highly optimized and very efficient. And this will also, it's a completely different approach to constructing direct solvers to boundary integral equations. So this is something that Shiv Chandrasekaran was doing with a student at UC Barber. You can do the same thing with these HBS representations. So instead of using this recursive application of Woodbury, you can sort of roll it out, form a big sparse system that involves, that connects all these various variables. The original sources, the potentials you seek, or I guess the other way around in a direct solver, but then also all these compressed variables. So just extend your vectors of sources and potentials with these extra variables. Then the corresponding coefficient matrix contains all these operators that we've constructed. So you still need exactly the same compression mechanism. You need to construct all the U and the V matrices, basically, and find the index vectors. But then once you have these things, instead of using this recursive application of Woodbury, you can just feed it into OMFPAC or something. So this is something that Leslie Greengard and Ken Ho did. And then the third thing here, so let me mention something else that Ken Ho has been working on in collaboration with Leshing Ying, is that, and this is very recent, but it's an interesting idea. So in this case, where you have uniform distributions of points, more or less in the plane, just to take an example. So the issue is that once you skeletonize, so recall that you get, the reason we get superlinear complexity is that we have an aggregation of points along the boundary. Right now, so their idea is, so before we go to the next coarser level, let's introduce some auxiliary levels on the same sort of half levels. So next, we shift. So we put a secondary grid, let's say shifted a half grid spacing. Like this. And now you compress. And now you see that these whole clustering of points here, these points used to be exterior on the original mesh, but now they're interior. So you can sort of skeletonize again and get rid of them, so that only a small number of points survive. And this appears to be reasonably straightforward to implement and could potentially also be a different way of getting to linear complexity for these methods. I'm going to describe a slightly different approach tomorrow, but you can actually keep pushing on this skeletonization idea that I've described today to improve the complexity. Then high-frequency scattering. I'm putting this bullet point in. There are two reasons. One is to remind you that these schemes will emphatically not have linear complexity if you shrink the wavelength as you increase n. So if you look at, say, a fixed geometry and you increase n in a way that keeps the number of points per wavelength constant, then there will be nowhere near linear complexity in this case, because ranks at the higher level will grow. So there's some very recent work by Erik Mikkelsen that has been sort of using the same ideas, but instead of having low rank interactions between distant boxes, you use some generalization of the FFT, so things called butterfly algorithms. And this is very recent. I don't even know if it's published yet, but yeah, it's very interesting recent work in this direction. And here's just a list of various things we've been doing in our group. And we will pick up here tomorrow and go revisit, talk more about the nature of these compressed representations for all the patches, the nature of the basis matrices, and so on. Any questions?
Can you go back one slide? On the, I've never heard of the roll up the FMM into a block sparse matrix. How does it scale for high frequency?
I have no idea. No, it's certainly that, no. For high frequency, it scales poorly, but even for situations where, even for the situations I've talked about here, I have no idea how it performs. I think it was only published in the dissertation of this guy.
It must not have worked. No one picked it up.
Well, in that case, it's sort of.
If you just feed in the sparse matrix into umfac, in 3D it scales as n squared. And 2D it scales as n to the 3 halves.
Yeah, but they were looking at special things like, a set of like elongated scatters. If you have a spiral, say, in 3D. So you have there's some reason to believe that it will be better than the worst case. In the worst case, it will certainly scale very poorly. But yeah, I just found it such an interesting idea, and it's easy from a software coding point of view. So, but yes, I've asked Shiv about this a couple of times, and he keeps telling me, oh, it works really nice, and I just have to find a student to pick it up. So I'm hoping at some point he or somebody else does look into it in some more detail. I'll be very curious to see how it performs.